Welcome back, everyone. In this lecture, we're going to talk about corner detection. When thinking about corner detection in computer vision, we should first ask ourselves, what is a corner? What defines an actual corner? Formally speaking, a corner is a point whose local neighborhood stands in two dominant and different edge directions. Or put simply, a corner can be interpreted as the junction of two edges, where an edge is a sudden change in image brightness. Now, there are various corner detection algorithms. We're going to take a look at some of the most popular algorithms, specifically the Harris corner detection and the Shi-Tomasi corner detection. Harris corner detection was published in 1988 by Chris Harris and Mike Stevens. The basic intuition is that corners can be detected by looking for a significant change in all directions. So here we have an example of a corner in an image. So we have two edges, and when they meet, there's our corner. Now let's imagine we started scanning and searching the image, looking for corners. Shifting this particular blue window that we have on top of the image in any direction would result in a large change in appearance if that particular window happens to be located on a corner. Flat regions will have no change in any direction. So if this particular window happens to be outside of something that contains any edges or corners, then we call this flat because there's no change as you scan in any direction. If you're on a particular edge, you're not going to have a major change along the direction of the edge. Which means our general intuition, and here we see the actual formula for corner Harris detection, is that if we're scanning the image with a window, just as we would with a kernel, and we notice that there's an area where there's a major change, no matter in what direction we actually scan, then we have a good intuition that there's probably a corner there. It's not just an edge, because an edge, remember, that still won't have much of a change along the edge direction. If we actually have a corner, then if we start moving in any direction, then we're going to experience a major change. The Shi-Tomasi corner detection was published in 1994 by Jay Shi and C. Tomasi in their paper Good Features to Track. It made a small modification to the Harris corner detector, which ended up with better results. So it's actually based almost directly off the Harris detection algorithm. It just has a small modification. And what it does is it changes the scoring function selection criteria that the Harris corner detection uses. And the Harris corner detection uses that following formula here, where we have lambda 1 times lambda 2 minus k times the sum of both lambdas. Shi-Tomasi actually just reduces that to be the minimum of lambda 1 versus lambda 2. And you can go ahead and check out the resource links for a full breakdown of the actual mathematics behind these corner detection algorithms. What we're going to focus on here is the practical implementation of them with OpenCV and Python. Okay, so again, we're exploring how to use both with the OpenCV library. Be sure to check out the resource links, and I've included the original publications for each of those papers if you're interested in exploring the full mathematical details behind the corner detection algorithms. Let's open up Jupyter Lab and get started. All right, I'm in a fresh Jupyter notebook. I'm going to start by reading out some images. And the first one is going to be just a flat chessboard image. So we'll say CV2 imread, and then I'm going to call data/flat chessboard.png. And then I will say flat chess is equal to cv2.cvt color. And we're going to convert this to just be red, green, blue, so it doesn't look strange. Flat chess, and then cv2 color, blue, green, red to red, green, blue. Okay, so let's actually show what that image looks like. So we say, flat chess, and here's our chessboard. It's essentially flat. It's an 8x8 grid. And later on, we're actually going to talk about grid detection on how to detect grid-like patterns in normal images. But really, the reason we bring this up here is because there's some really clear corners to detect here. Essentially, where each of these edges meet, that's going to be, well, I should say where each of these squares meet, that's going to be a corner. Versus the edges themselves, that's just an edge. So we have clear corners and clear edges, and we're going to compare to see how the algorithms work to find those corners. Then what I'm also going to do is load this up in grayscale. So I will say gray flat chess is equal to CV2 CVT color, call the flat chessboard, and then change this to color underscore, and this will go to BGR to gray. run that, and let's show you what that looks like, although you probably have a good guess of what it looks like. It's essentially just a grayscale version, which if we do CMAP is equal to gray, then we can see the grayscale there. All right, so we have this flat chessboard in color and this flat chessboard in grayscale. I'm also going to upload a picture of a real chessboard. So let's load that up as real chess. We will say real chess is equal to CV2 image read. I'm going to say data and then call real chessboard.jpg and then say real chess and fix the color on that one just so we can visualize it. CVT color, real chess, CV2 color, and this is blue, green, red to red, green, blue. Show that image. And here we have the real chessboard. So this one's quite a bit more complicated than just a flat image. The flat image, it's pretty obvious where the corners are going to be. So we should be able to detect all these inner corners. The ones on the actual edge, we're probably not going to be able to detect those just because it's at the edge of the image, but we should at least expect to see that this inner grid, all the corners will be detected. For this real image, it's actually going to be a little bit harder because there might be defined corners in the actual pieces themselves. So we should be able to define corners in the actual board, and then we'll probably also find corners in the pieces themselves. So for example, the rooks here on the edge, it looks like they have square corners, and maybe you can even think of the bishops as having corners because it's essentially a not such a high resolution image. So what maybe a curve actually looks like a corner. So it'll be fun to explore this image as well. And let's make a grayscale version of this one as well. So we'll say gray real chess is equal to CV2 CVT color. And then we're going to pass in the real chessboard and say CV2 color underscore BGR to gray. And then I will say PLT imshow gray real chess CMAP equals to gray. And as you might have expected, it's just the grayscale version of that chessboard. So now that we have our images, let's actually apply Harris corner detection on both of them, see how it performs, and then we'll also apply the Shi-Tamasi corner detection from the Good Features to Track paper. So what we're going to do here is the following. We'll say gray as a variable, and we're going to convert the grayscale image to float values. Because if we look at the one we have right now for the gray flat chess, right now they're all integers, and we're going to need them to be floating point values for the corner Harris detection algorithm. So what we're going to say is gray is equal to NP float 32, and then just pass in the gray flat chess. So we'll do the flat one first, and if we take a look at gray now, it's the same values. Now they just have a decimal point, so they're floating point values. Then it's time for the corner Harris detection algorithm, and this one's actually pretty straightforward. You say the destination variable name, then CV2, and then call corner, and we'll say corner Harris. You provide the source image. In our case, it's that grayscale image. And then you have a couple of parameters. The block size parameter is essentially the neighborhood size, and that's how it actually detects the corner eigenvalues and vectors. So a common block size to choose is 2, but this is something else you can experiment with. So we'll say block size is 2. And then we have k size as the next parameter. K size is the aperture parameter for the Sobel operator. So previously we talked about Sobel operators and X gradients and Y gradients. So the corner Harris detection algorithm actually uses that, and part of it is going to be the kernel size for that Sobel operator. So we'll say K size is 3. And then we have the K value. That's just K by itself. And this is the Harris detector free parameter. And I would encourage you to see the formula in the documentation string. So if you actually look at the documentation string and do Shift Tab here, it will actually show you the full formulas for this. So this one that we're looking at right now, that's the Harris detector free parameter. What we're going to do is we're just going to keep that to 0.04. That's a pretty good default value usually, but again, you can adjust these as necessary, starting off from these defaults and then moving up if necessary. So that's going to be the corner Harris detection algorithm. And then the result is dilated for marking the corners. So it's not important to the actual corner detection. This is just so we can actually plot out the points on the image below. So what I will do is I'm going to take that result and then say DST is equal to CV2 and dilate. And dilate is just a morphological operator, just as we discussed with erosion. So we're going to dilate this just a little bit. None is the second parameter we pass there. And again, this doesn't really have much to do with Corner-Harris detection algorithm. It's really just so I can show you the results. So what we're going to do is there's a threshold for an optimal value, and it may vary depending on the image. What we're going to do here is the following. I'm going to take my original flat chessboard image. Remember, this is the one in color. And then I'm going to say the following. I'm going to say wherever the result or the destination result of my Corner-Harris algorithm is greater than 0.01 times the max value. So let's think about what this is actually doing. 0.01 times the max value, that's essentially 1% of the max value. So wherever my result of the Corner-Harris is greater than 1% of the max value, what I'm going to do is reassign that to be equal to the color red. Now remember 25500, this is just RGB channels. So I'm saying wherever at the result of this Corner-Harris image, the actual image had a greater than 1% of its max value, then that's a corner that was detected. Again, this is really just for visualization, and you have to do this dilate process first to do that visualization. So we run this, and now let's see the results. Okay, and there we have it. We were able to detect all the corners inside the internal image. These corners on the edge, unfortunately, it's not able to detect those because if you think about it, there's nothing else on the edge for it to see into. So it just sees essentially a flat space. So all of this on the outside, according to the Corner-Harris detection, that's all flat space because it didn't see the other edge that is technically on the border or on the outside. What we could have done is then filled out maybe our own custom edge on the very border and detected those corners as well. But for the corners that are there, it looks like it was able to detect them perfectly. Again, just by using this little formula, we went ahead and marked them all as red. Okay, now let's try it on the actual real chessboard and see how that performs. So we're going to do the same thing here. I'm going to say gray is equal to NP float 32 and pass in gray real chessboard and say CV2 Corner-Harris source is equal to gray. And I'm going to be using the same parameters as I did last time. And I encourage you to use these as well and then adjust as you need fit. So K size, we'll say 3, and then K is equal to 0.04. Okay, so these are just kind of default values that we're using here. So we're going to run that. And then in order to actually visualize this, we'll say CV2, dilate, DST, none. And then what we're going to do is do the same sort of thresholding. We will say real chess, DST is greater than 0.01 times DST max and set that equal to red. So 25500. Okay, so now let's see where it found corners on that real chessboard image. And you'll notice now it's detecting way more corners. So luckily for us, it detected all the major corners on the actual chessboard. What's interesting is it actually didn't detect the corners on the outside right here. So it didn't think those were corners enough. And I can see how it could think those are flat. It's not as obvious as the dark and white tiles here on the chessboard, but it also detected a lot of corners on the black pieces. That's something you're going to have to keep in mind as you work with Harris corner detection, especially if you didn't think it was going to actually record those pieces as having corners. All right. In part 2, what we're going to do is expand on this and show you how to perform the Shi-Tomasi corner detector. It's a very similar process, and in fact, I think it's actually a little easier to use, but we'll go ahead and explore it in the very next lecture. I'll see you there. Okay, here we are back where we left off last time. In the previous lecture, we went ahead and showed you the Corner-Harris detection algorithm, and we marked the corners on both a flat chessboard and a real image of a chessboard. Now what we're going to do is use the Shi-Tomasi algorithm, and that one came from the Good Features to Track paper. And what's kind of funny is in OpenCV, the name of the function is actually Good Features to Track. So they just use that whole title. I went ahead and reloaded all the images since last time we drew on the images. Now I'm going to reload them. So I have real chessboard, flat chessboard, and then their grayscale versions. What we're going to do is actually call the Good Features to Track function. We're going to say corners is equal to CV2, and just start typing out GOO, and you should be able to tab autocomplete for good features to track. So that's the name of the function. And then we're going to pass in the grayscale version. So in our case, it's gray flat chess. We'll start with the flat chessboard 1. And the next parameter we provide is the maximum number of corners we want. So this is the maximum number of corners to return. That's actually really convenient because we can decide, hey, I only want 10 corners returned from this image. And it's going to choose the 10 best corners it sees. So based on a quality level parameter that we describe, then we're going to go ahead and do that. So let's pass in just 5 corners right now. Then the next parameter is a quality level parameter. So the way this works is the parameter value is multiplied by the best corner quality measure, which, if you look into the mathematics of it, is the minimal eigenvalue, or essentially the Harris function response. Don't worry too much if you didn't end up reading the papers and are just concerned with some good default values. Some good default values are 0.01. And then the next parameter, if you take a look at Shift Tab, is going to be beyond the quality level, the minimum distance. And in that case, another good parameter by default is 10. And then we can kind of play around with that. Okay, so we have our default parameters. The one that you're probably most concerned with is the second one, how many corners to detect. If you do not want a limit on the maximum number of corners, you can just provide a negative number. And it's going to return back all the corners it thinks it found. But for right now, I want to show you the results of this. So we'll just say detect 5 corners using the good features to track paper. Then what we're going to do is we're actually going to draw on little circles where it found the corners. The downside to using the good features to track, even though it's a little more convenient to use because of its kind of easier to understand parameters, the downside is it doesn't automatically mark the corners like the Corner Harris algorithm did. So what we will have to do is actually flatten out the array and draw little circles on it. So let me show you how to do that. First, what we're going to do is, if we take a look at corners, right now they're all floating point values, and we need them to be integers. So we will say corners is equal to np int 0, and then pass in corners. And that will automatically make everything into an integer. That will later on allow us to actually draw circles on this. So let's actually do that now. We will say for I in corners, what we're going to say is x comma y is equal to I dot ravel or ravel. And that's essentially kind of flattening out that particular array. And then we're going to draw a circle on that. So we'll say circle, and we're going to draw it onto the flat chessboard at xy. And then we'll just provide some parameters here. We'll say 3, and then the color can be red. So 255, 0, 0, and then -1. We'll just have it filled in for thickness. So go ahead and run that, and then let's see the results on the flat chessboard image. So when we run this, now I get to see those 5 corners it detected. So now let's try actually trying to find way more corners. I'm going to change this 5 to be something like 64 and rerun this. And there you can see it's detecting all the possible corners. And it should have detected less than 64 here, but it returned back all the best corners it thought that it found. Okay, now let's actually try running this on the real image and see how it performs. We're essentially going to do the same thing. In fact, I'm going to copy a lot of this code. So we're going to start off with corners. And then instead of gray flat chess, we're going to say gray real chess. And in this case, let's go ahead and find more than 64 corners. We'll find some corners off of the pieces as well. So we'll say something like 80. And we'll keep the same default values for quality level. Go ahead and run those. And in order to mark the corners, we'll be doing the exact same thing as last time. Setting them as integers. And then copying and pasting this for loop that actually draws the little circles for us. So copy that. Paste it in here. And then let's go ahead and show the result. We'll say plt imshow and real chess. And whoops, looks like I accidentally drew it on flat chess. Let's run this again and draw it onto real chess. There we go. And there you have it. So these were the corners it detected. You can see, notice now that it actually didn't detect some of the major grids on the actual chessboard itself. So that's probably a good indication that you would begin to need increasing this to maybe detect some more corners. So now if we ask for 100, you'll notice now it begins to detect some more corners along that board. However, as you ask for more and more corners, it's probably going to begin detecting more and more on the actual pieces themselves. Okay, So that's how you can use the Shi-Tamasi algorithm from the good features to track paper. It's really quite simple. You just say good features to track, and then you pass in the image that you want to find the corners. You pass in the maximum value of corners, and then your other parameters, which you can default to 0.01 and 10 and adjust as you see necessary. Then if you actually want to draw circles onto where you found the corners, just convert it to integers, and then for I in corners, you go ahead and flatten that out to get the actual coordinates of the corners themselves, and then draw little circles on them. And notice I draw it back onto the real chessboard, not the grayscale one. And then we have our real chessboard with little circles wherever we found corners. Okay, thanks everyone, and we'll see you at the next lecture where we begin to discuss edge detection.